Welcome to St. Clair Chemistry. In this episode, we're going to be talking about mass spectroscopy. Now, mass spectroscopy will tell us or lead us in the direction of determining the masses of elements, isotopes, and compounds, and looking into their structures. It's really an interesting subject. I hope you enjoy today's episode. When we look at mass spectroscopy, the first thing we want to do is look at the purpose of mass spectroscopy, and the purpose is that it produces a spectra of masses from the molecules in the sample of material and fragments of the molecules. It's used to determine the following: the chemical composition of a sample, the mass of the particles and of the molecules, potential chemical structures of molecules by analyzing the fragments, the identity of unknown compounds by determining mass and matching that to known spectra, and the isotopic composition of elements in a molecule. So the first thing we ought to do after we kind of know what a mass spectroscoper the first thing that we ought to do after we know what the mass spectroscopy device does, or the mass spectrometer, is look at kind of the internal workings of it. So we have an ion source, a magnet. The magnet will separate out the different isotopes or elements because lighter elements will deflect less than heavier elements, and so on. And we have some kind of a capture device. So if we look at the stages of this, we have an ionizer, and that's down in the ion source, which converts some of the sample into ions. It doesn't convert all of it, but some of it into ions. The mass analyzers will separate the ions according to their mass to charge ratio, and the detector records either the charge induced or the current produced when the ion passes by or hits the surface. Some mass spectrometry methods is electron impact, chemical impact, electrospray, fast atom bombardment, and metric assisted laser description. And we can see kind of what they're looking at if you look at the mass range and what they're trying to find. When you see in that chart CG, that is gas chromatograph. Everything else you read through and kind of see it, but as the molecules get bigger, there has to be different devices to use in order to pick up the mass range. So if we look at this sample spectrum that we have here of carbon dioxide, you will see on the y-axis the relative intensity. Along the x-axis is the mass to atomic number, m to z, or m per z. So that kind of gives us a ratio, and then we have different heights of these columns. So if we were trying to read this mass spectrometer, what we would look at is that we have a very large molecular peak at about 44 or at 44, and that would compare to the mass of CO2 plus ion, because carbon is 12 and it has a mass of 12, and oxygen has a mass of 16. So that would be 44, and then the plus, remember the electrons are so small, we don't count their mass, but that's what that peak would be. And then there are some other fragmented peaks. These are these smaller peaks. And so one of them compares to CO, and one of them compares to oxygen plus, One of them compares to carbon plus. And remember, when they go through the ionizer, it is capable of breaking apart the molecule. So that's why we see all these small peaks, and then we see a big peak, which is the bulk of it is on the big peak. If we look at bromine, and bromine, there are two isotopes of bromine, which means that there's bromine with two different amounts of neutrons. And they're 57 or 50.69 and 49.31% respectively. And so when we look at this graph, we will see that the large peak is the combination, and if you take 81 and 79 added together, it's 160. That's why that's a large peak. And then we see a smaller one where, because it's Br2, we could have one where we have two bromine 79s, and the other smaller peak is two bromine 81s, and then this peak around 80 is a fragment where the bromine broke apart into elemental bromine or ionic bromine, and we have 79 Br plus and 81 Br plus. Now, if we look at methyl bromide, you see the chart. And so the tall peaks would correspond to CH3Br. When we look back at the peak of between 0 and 20, that's probably going to be CH3 plus. And so you can analyze out what all of these things were based off of masses. And that's what somebody who really would read these for a living does, is that they look at all the possible peaks. Methylene chloride, as we see here, look at these yourself. You can see that we have a tall peak around 40, close to 50. And so that is actually probably going to be a fragment of CH2Cl. And then the ones around 80, 80 to 90, you're looking at the methylene chloride still together. So most of this actually does break apart. We look at vinyl chloride, so CH2CHCl. So the peaks are between 20 and 30 are going to be CH2CH without the Cl. The peak at 35 is a Cl minus by itself. Then the large peak around 62 is going to be the full vinyl chloride, and then you can see the different isotopes where they would fall on this chart. Now, if we have, for example, codeine, which is a large complex molecule, it has all kinds of fragments. And that's not something we would look at in here. That's not something, researchers look at something this difficult. On practical applications, you wouldn't be asked to look at something like this. Now, toluene here, C7H8, has a couple of different structures that we have to look at when we look at these. So when we look at this, we can see the peak at 92, how toluene looks, and the hexagon shape with the CH3, that's the shape of toluene. And then the one at 91, a hydrogen has been removed in the process. And then we have some fragments where we've removed the CH3 group, or in this case, it broke apart and made a cyclohexapentadiene group. Then we have a C4H3, just another grouping off of these things that show up when we have these fragmentations. So part of the problem is just kind of having to read where things fall. The molecular ion peak is not the dominant peak of the spectrum. So the molecular ion is the one that's pointed with 92, and yet it's not the tallest peak. And that happens sometimes. You just kind of read it and see what's on there. Now, if we're talking about forensics, this is where mass spectrometry really comes into play. So mass spectrometer is used to confirm the identity of unknowns, such as illegal drugs. Unknowns are often not pure and must be separated from the mixture. A gas chromatograph is used to separate the components of the mixture, and then the mass spectrometry fingerprints these components once they're separated so that you actually can look at it. So if we start out with our mixture of circles, ovals, squares, stars, and then we run it through a gas chromatograph, we can separate those into square, star, circle, oval, and then the mass spectrometer can actually give us the sample of each one, and then you can look these up on charts, they're online, or you start figuring out where your tall peaks are, you can get a mass, and then you can start working backwards to figure out formulas and what compounds that we have. And it's like anything else. With practice, you start figuring these out. But this is what happens on like a CSI show where they run this gas chromatograph and then they run a mass spectrometer and they come up with some big convoluted symbol, and the technician goes, oh, that's a chocolate bar, or that's codeine. And they know that in real life because they've done it a lot of times, or because they've looked it up to figure it out. Isn't it fascinating how compounds and elements, we can determine their mass using mass spectroscopy? I trust that you enjoyed today's episode, and thank you for tuning in to St. Clair Chemistry.